So welcome back to introductory course on CFD. Today we are going to start with governing equations of CFD. So to begin with, let us understand what is that we are going to learn in this particular chapter. First one, we will be understanding and differentiating forms of governing equations, which is conservative forms and non-conservative form of equations which we come across in CFD. So we will be able to define what are these forms of equations, and we'll try to differentiate between these two and application of these forms of equations in CFD. Next, we will be concentrating on rewriting them in simplified forms according to our requirement, which are called suitable forms for forms of equation for CFD. Suitable form of equations for CFD. How we can rewrite all the forms of equations which we derived in earlier sessions, that is continuity, momentum and energy equation, so that all of them are brought to a single platform or single form of equation, and complete flow field can be solved directly by using these forms of equation. Then we'll proceed with shock fitting and shock capturing approaches, which is specifically deals with supersonic flow over objects wherever there is formation of shock waves. How to solve those kind of problems, especially these are the characteristics which involve discontinuity in the flow. So till now whatever we studied were limited to continuous flows, but this kind of approach where we have discontinuity in the flow, so to solve them we can use these kind of approaches. Then followed by identifying nature of partial differential equation based on the governing laws. So this is going to be most important aspect of this particular chapter, where based on the nature of the partial differential equation we will be able to create an approach to solve them, or we can come up with an approach to solve them. At the same time, we will be able to predict the behavior of the flow based on the nature of the partial differential equation. Then we will try to apply various methods to predict the nature, which is eigenvalue method, Cramer's rule and matrix inversion method. So matrix inversion methods can be done along with the eigenvalue method. Then we have Cramer's rule, which we come across in matrices to predict the nature of the partial differential equation. We apply these techniques to predict the nature of the partial differential equation. So let's dive into the first chapter, which is conservation and non-conservation forms of equations in CFD. So conservation form, these are the session outcomes. So we will be able to define conservation form of equations, define what are the non-conservation form of equation and differentiate between those two. So conservation form of equations. So these are expressed in form of flux. So directly these are derived from control volume fixed in space in form of integral forms. Then they will be reduced. This will be reduced into partial differential forms. So since these are directly derived explicitly using the fixed domain approach, these equations do not have any exact differentials. So these have only partial differential terms along with divergence term. So you can see this is the divergence term and this is the partial differential term in time. So they are directly derived from the physics of the problem, where we consider the mass to be stationary with respect to the fluid. So mass is considered to be stationary. So Hence, all the conservation laws can be applied here. So as I said, this uses finite volume method, which is mostly fixed in space. Based on this, we'll end up with, as we already learned, that this form of approach will always lead to integral form of equations. So based on the integral form of equation, when we reduce them, we'll end up with these form of equations. So this is what I was mentioning. So derived from integral form of governing equations, and this approach ensures conservation of mass, momentum and energy. All three parameters, all three governing equations are in conservation form. So that means mass, momentum and energy equation are considered to be fixed. The control volume is assumed to be fixed, so the mass, momentum and energy are always conserved, unlike the other case. So these type of flow equations are very much suitable for discontinuous flows. Then we have fluxes across control volume boundaries. So they account for changes in the fluxes across the control volume. So because of that, these are most commonly employed in the flow fields where there are discontinuities. So they ensure global conservation, because as I said, fluxes across the control volume are taken into account, and because of that, all the conservation laws are applicable here. Hence it ensures the global conservation of all the parameters, whether it is mass or momentum or energy, all are considered for conservation. Next, non-conservation form, these are substantial derivatives. These consist of substantial derivatives, and the control volume or the infinitesimal element, the fluid model, is assumed to move with respect to the fluid. It is not stationary. Hence, we can say it is non-conservative form of equation. So these do not account for changes, complete conservation of properties. For example, you take continuity equation, d rho by dt plus rho into divergence of v is equals to 0. So it is somewhat different from whatever we discussed continuity equation just now, which is dou rho by dou t plus divergence of rho v equals to 0. It is quite different from this. This was having a partial differential term, whereas this is substantial derivative. So which accounts for total changes. So this form of equations, we call them as non-conservative form of equation. They do not account for the flux changes across the domain. Since the object itself, since the model itself is moving, they cannot account for all the fluxes and variation of properties. Hence, they are called as non-conservative form of equations. So it is always in differential form. To be precise, substantial derivatives are involved, and it is mainly considered for point-wise changes. So it will be mostly for infinitesimal element approach. So you always end up with differential form of equations. So as I said, infinitesimal element always uses Lagrangian approach, where the element is assumed to move and all the characteristics of the element are noted, and based upon the characteristics of that element, the governing laws are developed. Now, these are derived from using chain rule and focuses mostly on primitive variables like velocity and pressure. So interpret physically, and these are less accurate when there are discontinuities in the flow. So when compared to conservation form, which are suitable even for the discontinuous flows. These are certain differences between conservation and non-conservation form of equations. So they have, the conservation form have divergence of fluxes. We call them as divergence form or divergence equations. Conservation form can also be called as divergence equations. Whereas non-conservative form has expansion using product rule. That means we have d rho by dt plus divergence of rho v. Then we have to expand this. Then only we are going to get the result. And these always involve substantial derivatives. When coming to numerical conservation, conserves flux exactly in the discretization, and they may not conserve. That is, as I said already, the fluxes are taken into account wholly. That is, global conservation is taking place or considered in conservation form. So that may not be possible with non-conservation form because of the movement of the domain itself. So it can capture anything, especially shocks can be captured using conservation form of equation, but using non-conservation form of equations, there can be smearing effect which always leads to oscillation near the shocks. So we cannot capture the shock that much easily when we are going for calculation of supersonic flows, especially involving shock waves, because shock acts as a discontinuity. So non-conservation forms have difficulty in predicting the discontinuities or solving the flows where we have discontinuities in the flows. So applications you can use for non-conservation forms can be smooth without shocks. That is, whenever you have continuity, then only you can apply non-conservative forms or non-conservation forms. But conservation forms can be used for various cases apart from shocks. That is, any type of compressible flow you take, whether it is formation of shock waves or not, this can be applied very much easily. And we can solve even turbulent flows around the bodies using non-conservative form of equation. So that is the end of the session. Thank you.